section, we will be doing some molecular shapes, some more bonding, hybridization, and we'll be drawing loose dot structures as we go through the shapes. I'm going to help you to redraw them and know the little exceptions here and there. And of course, then we're going to be getting into a lot of shapes you've never seen before because we didn't teach them last year. So I'm going to kind of go a little faster through the stuff that you know, and so we can get to the stuff that you don't know. Like the shape of the molecule plays an important role in its reactivity. Noting the number of bonding and non-bonding electron pairs, we can easily predict the shape of the molecule. Okay? Bonding and non-bonding. So write quickly in those blanks because we're moving on. All right. Simply put, electron pairs, whether they are bonding or non-bonding, lone pairs are the non-bonding ones, they're going to repel each other. So they're going to spread out around the central atoms. By assuming the electron pairs are placed as far apart as possible from each other, we can predict the shape of the molecule. So, non-bonding are lone pairs. Bonding pairs are when an atom is attached to the central atom. Okay? So keep that in mind there. Now, we can refer to the electron pairs as electron domains. So you have bonding pairs, non-bonding pairs that give you electron domains. Now, in a double or triple, we consider that to be one domain anyways. Now, it does, we'll get to it later, but the double, triple bonds do affect the angles slightly, but not hugely dramatically. Valence-Shell electron pair repulsion theory is the VSEPR theory, and this is why we do what we do. It's the best arrangement to minimize those repulsions. So we space them as far apart from one another around the central atom as possible. As far apart from each other as possible. Valence-Shell electron pair repulsion theory. And you might see that abbreviated in a question with the VSEPR abbreviation, so you should be able to recognize that it's referring to shape when you get to that point, okay? Now, the electron domain geometries go from 2 to 6, so it depends on how many you have. Linear things are going to have 2, where 6 things would be in your octahedral category, okay? Around the central atom. And when I say things, I'm talking about bonded pairs and the lone pairs. Non-bonded pairs count as being a thing that could be spaced around the central atom, okay? So for electron domain geometries, even though we know that ammonia is a trigonal pyramidal shape, that is its shape, but it actually belongs in the tetrahedral domain because it has 4 things around the central atom. 3 of them are the H's, one of them is a lone pair. So it has 4 different electron domains around the central atom. It's in the tetrahedral domain, but its shape is pyramidal, which we'll get to, okay? So the domain and the shape don't necessarily have to agree, okay? So once again, reiterating that fact, even though that this one is under the tetrahedral domain, it does show a pyramidal shape. Now, within each domain, there can be different types of shapes or geometry, molecular geometry. So this would be under the tetrahedral domain, which would have 4 things around the central atom. You could have tetrahedral, which would be 4 bonded atoms. You could have a trigonal pyramidal, which has 3 atoms bonded and 1 lone pair. Still 4 things around it. And then you could have a type of bent where you have 2 bonded atoms and 2 lone pairs. Okay? And this one would fit all under that tetrahedral domain. Okay? So keep that in mind there. So before we can get to the shapes themselves, we have to understand hybridization of the orbitals. Okay? And how those, since the S and P's and D's have to overlap, they form hybrids, mixtures of the different orbitals. Okay? When they're forming these bonds. So one type of hybridization is when you have an S and P together. The S's and P's overlap. You get what we call a sigma bond. And the sigma bonds are all formed for all of our single bonds. It's always an S and P that's going to overlap in a single bond. Okay, for the sigma bonds. So anytime you see a single bond, you know sigma. Okay. Now the pi bonds, okay, are characterized by a side-to-side overlap of the p orbitals. So what I would like to explain this, because you know our p's, we have the px, we have the py, we have the pz orbitals. Okay? If this is referring to the x-axis, then these would be p orbitals that are on the y, right? And this is where they're going to overlap and hybridize. So, and you're going to have these show up when you have double bonds, and you'll have two pi bonds in the triple because there'll be another one on another plane. So if the SP is forming the single bond, a sigma bond on the x, then you would have a pi bond that's on the y-axis and a pi bond that's on the z-axis, forming the other two if it was in a triple bond. Okay? So keep in mind that this is like the upper sides of the dumbbells are now mixing together, forming a hybrid. Okay? And I put the diagram on your paper there to help you see that in a single bond you're going to have one sigma. In a double bond, one of them is a sigma and one of them is a pi. And then in a triple, you're going to have one bond that's sigma and two that are pi. And that's how they hybridize there. So knowing that is important because we're going to be using these hybrid orbitals when we're forming multiple bonds. This one is acetylene. Really structurally, or Lewis dot structure wise, it's going to have a triple in it. So it's showing you right here. Here is the single bond, the sigma. Then you have one overlap for the first in the double and the triple there. Then the other one is on, it's behind there, you can't see it very well, but that was the other pi bond forming the other part of the triple there. Okay? That's one type of hybridization that you do have to know. They can ask you a multiple choice question, you know, which one has the most pi bonds in it, which one has the most sigma bonds in it, and so forth. Okay? They like to ask those kind of multiple choice questions. Now talking about shapes and Lewis dot structures. The linear domain, there's only just the one linear. Now you can have a couple different arrangements of linear. You can have two atoms together because point A to point B is always going to be linear. You can have ones that have three atoms in it, like carbon dioxide. And there's a special exceptional case with beryllium in it. Okay. But let's talk about their hybrid orbitals when you have linear shapes. Mixing the S and P yields two degenerate orbitals that are hybrids of the two. So when you have one S, one P mixing together, you're going to get an SP hybrid. SP hybrid. So basically, here's your S, here's your P, and they form two of these guys that are mixed together of the S and P. So it's kind of like a red and a blue make purple. You're mixing them together. And they get a new shape out of it. Kind of looks like the P if you ask me, but okay. So you're going to get an SP hybridization when it's linear. And here's showing you that you're going to have two of them because this is one of your overlaps here, an SP here, and here would be the other SP. And this is for beryllium dichloride, Like I said, that's an exceptional case because beryllium doesn't need a complete octet. Okay. So let's get on with that and start drawing some fun stuff. Starting with the easiest one, of course. Which one do you think is the easiest one? HF is the easiest one. You're right. Okay, but we need to revisit some of our rules here. What is the first thing that you do when you're drawing a Lewis dot structure? Valence electrons. You got to count them because that's what Lewis dot structures are representing, the valence electrons. So in HF, how many valence electrons does my hydrogen bring in? 1. How many does the F bring in? So I have a total of 8 valence electrons I get to work with here. Now, the other thing you need to note is the special exception of hydrogen. Hydrogen needs how many to be satisfied?
2.
Only 2. So hydrogen never can be a central atom. It's always just a ligand. It's attached to something else. Okay? So you never ever want to put hydrogen in the middle. It only needs 2 to be like helium and stable. Okay? So the second thing after you've calculated your electrons is to attach them to one another by a single bond. So if I attach them by a single bond, how many valence electrons does that mean? 2 are now used. So now I have 6 left. Now I need to look at satisfying the octet of the atoms. Usually you do the ligands, but here there's no real central atom because it's just HF. So who needs more electrons? F. And it needs 6, 2, 4, 6, 8. Now make it nice and happy with its octet. Now we have 0 electrons. And if you were to draw the ball and stick model, it would look something like that. And of course it's linear. What is the degree angle on a linear molecule? 180. It's a straight line, so you're going to go with 180 there. Okay. Now we also have to look at polarity. What do we look at when we're determining whether the molecule is polar or nonpolar? Symmetry. Okay. Obviously not symmetrical, but we also wanted to draw in a dipole moment. Which way is it going to go? Towards the F. Okay. Because the F is the more electronegative element, it's going to be pulling, so you can look at them as where the dipole moments. If you have equal dipole moments going in the going out from the central atom, then your symmetry is telling you it's nonpolar. So this one happens to be polar. Okay. So now let's look at carbon dioxide. My next favorite. CO2. Count our electrons. How many do we get for carbon? 4. Because it's in group 14 or 4A, or it has 2 in the S, 2 in the P. You decide how you count your electrons for valence. How many does each oxygen bring? 6 times 2, so that's 12. So now I have a total of 16 I get to work with. Now in this case, we have 3 atoms, so we have to decide on a central atom. How do we decide on that? Yes, it's carbon, but why is it carbon? Least electronegative element is the one that's going at the center, and of course it's not hydrogen, so it can. The next thing to do is to attach your ligands. In this case, oxygens are going to be the ones attaching as ligands. I know it's a lovely word. Okay, so how many did I use? So that's 12. Now if carbon is or silicon or central atoms here, usually that group, when you only have 2 other things to attach, they're going to end up being linear shaped. So I always draw the Lewis dot structures linear. Now yes, I'm programmed to do that because I've been doing this for a lot longer. But because when we get to the bent ones, how do I know to draw them bent? Because they're not carbon or silicon as the central atoms. So if it's sulfur, oxygen, or selenium, or nitrogen, if it's not a carbon, I know to draw it as looking more like a bent shape. Okay? So now that I've done that, I need to satisfy my ligands first before I go to my central atom. So 1, 2, 4, 6, 8, 10, 12. Oh, They're all gone. I used them all. But there's a problem here. Carbon only has 4 electrons. Carbon's not happy. So what we do is we take off one of the pairs and we double bond it. It's called a coordinate covalent bond. So I'm erasing that one pair and double bonding it. It doesn't matter which one you take off either. Okay. And I would need to double bond the other side. Now, why am I double bonding both sides instead of tripling one and doing a single on the other? Oxygen typically, in very, very rare few cases like carbon monoxide, will form a triple, but oxygen simply does 2 bonds because it has 2 lone pairs usually, so it's only going to form 2 bonds. So you wouldn't want to triple these, okay? But as you can see, it's linear shaped, straight line, 180 degrees, and if you want to count the hybrid orbitals, you just count them based off of the orbitals in the sublevels. So S has 1, P's have 3, and then D's, of course, we'll get to later, have 5, right? D1 to D5 here, whatever, okay? So each bond attachment to the central atom will take up one of the orbitals. So this is why, if you don't want to memorize that all linears are sp hybrids, you can do it that way and count the number ones, or count how many things are attached and how many lone pairs are on the central atom to determine the hybridization. That's one way to do it, or you can memorize them. So we get that sp hybrid. Oh, is this one polar or non-polar? You do the dipole moments. They both pull on the carbon equally, so the symmetry is even on both sides. It's symmetrical, so this would be non-polar. Now for the lovely beryllium example. Beryllium is one of those weird ones like boron. Berylliums you'll only see in linear molecules. They only need 4, so they only usually attach to 2 others, just so you know. So if we're looking at boron difluoride, okay, the Be brings in 2, the F's bring in 7 times 2, that's 14, so that's a total of 16 electrons we get to work with. So I attach them, once again knowing that it's going to be linear, because beryllium molecules are always going to be linear by definition. So my other 12 are going to go for what? What are the other 12 going to do? They're going to go around the fluorines, 6 each, to satisfy those octets. This is also linear, 180 degrees, sp hybrids, and also polar or non-polar. Non-polar, okay, very symmetrical. The dipole moments, if you were to draw them in, of course, would push towards the fluorines. Yes, question? Well, the hybrid orbitals are just the S and P that are blending together. So if you look at how many orbitals you need to blend, that's why, like, I need to blend 2 orbitals for linear, because I have two atoms forming this bond right here. Okay. So I'm only blending the 2 on either side. Now when you attach more things to the central atom, you have to blend more orbitals. So that's why we're going to, like the next one, when we have 3 things to blend, it's going to be sp2. And then the next one will be sp3, because you have to blend all 3 of the P's in there. Okay? So, because it just does that, it's one of the exceptions. It doesn't do a transfer, it shares. well, it likes to share this way. And metals don't typically share. That's why it's an exception. So I wanted you to see that why the shapes and the polarity matter here is really based off of the pull of the dipole moments. So if you have equally pulling, and that's why if your ligands are the same, you're going to be symmetrical, because they'll equally pull on the central atom, and therefore you will have a nonpolar molecule. Whereas things that are not symmetrical, like NH3 up here, where the dipole moments are all pulling towards the nitrogen up here, as you can see, they're pulling towards the nitrogen. This one would be polar and throws off the symmetry there. If the ligands are not the same, so you have three that are the same, one up here that's different, and of course the dipole moment pulls towards the stronger electronegative element, and it's going to be a polar molecule. Okay? So keep that in mind when you're looking here as to why the symmetry works. This is why the symmetry works. Okay? Now on to the trigonal planar electron domain. So in that domain, we need to have three bonded or non-bonded pairs around the central atom. So you can have trigonal planar, and you can have some variations of the bent. You can have two atoms attached with one lone pair on a bent molecule that falls into this domain. Okay? And for the hybridization, you get one S, you get two P's now blending together. So you're going to get sp2 hybrids. So here is your blue S, your two red P's. These are P's. Why did I put an R there? Because I said red. And they are going to blend to make the purple sp2s, forming that hybrid. Okay? And that's based off of the three things attached. If you looked at the way I was doing it before, this is the S, this is the P. So I have one thing attached and then two others attached. So S and two in the P. Okay? So three things attached means sp2 is going to be hybridized. Now, four things attached, then it'll be sp3 will be filled and so forth. All right, so I'm going to do a couple examples here of, and I made carbon dioxide. I didn't say carbon dioxide here if you wanted to see it. So nice linear shape. The bonds don't look linear, but the atoms themselves are linear, as you see. Okay, so what do you want to start with? Boron, the exception, or formaldehyde? Formaldehyde, okay. Let's start with formaldehyde, right here. All right, C brings in how many? The H's are going to bring in 2, and the O is going to bring in, that's a total of, who goes in the center? Who goes in the center? Carbon. Now, attach your ligands, and it doesn't matter which way you do that. I don't know why I like to put oxygen on the right, but you can put oxygen on the left. You can put oxygen down below. I don't care. Okay? It doesn't matter where you put them around it, just as long as it's around it. But when I did that, I now used 6 electrons, so now I have 6 left. Now you have to satisfy the ligands first. So we know the hydrogens don't need any more. Our oxygen needs them, so that's that 6. But I have a problem here. Carbon is unhappy, so I'm going to have to coordinate covalent bond that carbon. Take the one off, make it a double. When I do so, it allows me to create the flat triangle. As you see, it's a flat triangle. This is formaldehyde. Nice and flat. Okay? Yes, it's very toxic stuff, by the way, formaldehyde. They put it in, yeah, and it used to be used to preserve, like, the frogs for dissection and stuff, but because it is carcinogen, it's no longer in that stuff because we use formalin preserved specimens now in anatomy and biology. Okay? So it really does form ball and stick model, a flat triangle. That's a terrible double bond, but here, let me fix that. But yes, the oxygen would be larger, the carbon, and then, now generally, trigonal planar angles are usually 120 degrees. Usually. However, because of the double bond here, and there's more electron density here, it's going to push these guys downward a little closer to one another, and these end up being like, I think 114-ish or something, and these are like more like 124. But roundabout, trigonal planars are supposed to give you 120 as their spacing and their angles. But because of the double bond in this case, it does change the angle just slightly. Okay? Now for boron, and our exception here. We all know boron likes to have what? 6 valence electrons. BCl3. So, boron brings in 3. 3 times 7 is 21. That's a total of 24 that I have to work with. Right? Check my numbers. Okay. Thank you. Who goes in the center? Boron. Attach your ligands. Right? How many did I use now? 6, so I have 18 left. Now, boron already has 6. Remember, this is an exception. So write that down. Boron only wants the 6. So where do the other 18 need to go? On the CLs.
There are a lot of exceptions.
Pretty much, well, the exceptions are beryllium wants 4, boron wants 6, and then energy level 3 and above can do expanded octets. So we'll get to those in a minute, but they can do expanded octets. So, really ball and stick model wise, this one is going to be 120. Oh, we forgot to determine too about our formaldehyde. Is formaldehyde polar or nonpolar? Polar. Definitely polar. Your dipole moments shifting towards the oxygen there. Here, this is a perfect 120 degree angle because all the ligands are the same. So, and you don't have extra electron density due to a double bond. And that'll be 120. And remember, you have 3 things attached, so these are going to be sp2 hybrids. Okay? And this guy, all the ligands are the same. This one is going to be nonpolar. So all of the dipole moments are going to go out towards the chlorines, being the more electronegative element. Okay? Any questions on those typical trigonal planar type molecules? So, oh, it's 111. I was close, but as you can see, the angles are just slightly off. Not perfect 120s, but does give the general shape of the flat triangle. Okay? For the formaldehyde there. All right, non-bonding pairs and bond angles. When you have non-bonding pairs, those lone pairs, they do have a little bit more magnitude of taking up space. So they push the atoms closer together, so you will get a decrease in your angles. So when we get to tetrahedrals, you'll see 4 atoms attached, no lone pairs, 109 degrees. But when we switch to adding a lone pair for one of the atoms, it decreases the angle to 107. Right here on this pyramidal one. And then if you have a bent shape, which is our water, 2 lone pairs, lone pair, 2 atoms, it pushes the angle even closer to 104.5. But we're going to get to that now that we're getting into the tetrahedral domain. So those lone pairs actually take up more space than an atom, if you can believe that. Oh, so no, first of all, we got to do the bent example for the trigonal planars. And one of them's a very odd exception. And they've only put it on the AP exam apparently once, but you know, it's been a while, so they might recycle it this year. You never know. And that is our nitrogen dioxide. What is wrong with nitrogen dioxide? It only has 17 electrons, so that means you have one oddball. Yes. So NO2, 5, 12, that's 17. And how does this one really work? Here, let me show you. And we're going to have some resonance here, so pay attention.
I hate resonance.
I know, resonance is fun. So resonance, really, you're supposed to draw all the structures, but okay. So we attach our ligands. Now, how do I know to draw this one bent? Because who's not in the middle? And there's two things. It's not a carbon group one in the middle of two atoms. It's now a nitrogen or oxygen group one in the middle of two atoms. So I know to draw it bent shape. Okay? So I used 4. So now I have 13 left, right? The job is to satisfy the ligands. So that means there's this lone dot on the nitrogen. But there's also a problem because if I left it like that, nitrogen only has 5, which is highly, highly unstable. So I am going to coordinate covalent bond one of them, forming that double. So that means this guy has resonance. So you can draw it either way. The double bond can go on the other O. And technically the double bond isn't like on one of them. It's on all of them. And it kind of merges and delocalizes the electrons, forming kind of a hybrid orbital. And I'm going to show you pictures at the end of what this delocalizing looks like on these resonance structures. So this one does have resonance. And yes, it's a silly one, but it is the only one I know of where you're going to have this oddball 7th electron where the nitrogen only has 7. But it's better for you to know about it in case they put that back on there. Okay? And yes, so this one, and these are bent shape. And the angle is going to be probably greater than 104. Okay? Because you only have the one little dot up there, not pushing down so far. But it won't be linear. It will definitely be bent shaped. And of course, then we would say these ones are also polar. Dipole moments pulling towards the electrons. To the oxygen, technically it probably goes like that in between the oxygens, where it's pulling out towards where the oxygen side of the molecule there. Yes? Nope. It's the nitrogen that gets the 1. This is the way nitrogen dioxide just exists. It's a weird one. It's not the most stable. It's not a great molecule to also subject yourself to because it has this free radical. That's what we call it when there's missing part of its octet there. It's a free radical. So, and things with free radicals have a tendency to grab onto DNA and alternate, and that's why they're carcinogenic. Those free radical molecules. So I don't really want to go exposing myself to nitrogen dioxide all that much. What? It's not usually something they use. It's one of the things that comes out of the exhaust when it's burned, because in fossil fuels you have lots of sulfur and they're impure, and you get nitrogen coming out of them too because they're not perfect hydrocarbons. All right, now for nitrite. Nitrite's easier. Why is nitrite easier? We gained 1, so now we have 18 electrons, right? Because of that -1, we gained an electron, so now we have, it's basically the same thing except for that oddball is no longer an oddball, right? You got the 2 dots. But you are going to need your brackets with your charge. Don't forget those. And it is a resonance structure, so technically you are supposed to draw both.
draw the double bond on the other one?
What?
Why wouldn't you just draw the double bond on the other one? And get rid of the 2 on the nitrogen.
Because it doesn't form that way.
Okay.
And then you would have an extra pair of electrons. Because if you took this off and put it here, then this has 10. And oxygen can only have 8. Oxygen, carbon, nitrogen, and fluorine always only follow the octet rule with 8. So if you took this one off and stuck it there, that one would have 10. Yes? No, I have a meeting, but I will be here tomorrow after school. Okay, so same idea here. This is bent. It's polar, shows resonance. Like I said, the angle, not perfect angle here. It's not perfect 104.5. Probably be a little bit greater because you don't have 2 lone pairs. 2 lone pairs gives you the 104.5 on the bent. So it'd be a little bit greater than that. All right, so moving on to the tetrahedral domain. 4 things around the central atom. And they get 1 S, 3 Ps to form sp3 hybrids. Okay, as you can see now, you have 1 S, all 3 Ps participating to make 4 separate hybrids. Okay, 4 separate hybrids of sp3s. They all blend together and make this new purple hybrid, as you can see in the picture up here. These are the electron orbitals, yes. Well, within the cloud itself are all the specific little shapes, like the D shapes, the F shapes, but it would depend on which one you're dealing with. Yes. Like if we're talking about, say, you know, like arsenic, you're in the 4S and 4P, so now the ones that are hybridizing are the 4s, 4S and Ps. Okay? All right, so our tetrahedral example is very, very simple. All right, so how many here? Tetrahedrals are pretty easy, so I'm going to go pretty quickly through those. So, who goes in the center? Attach your 4. So I just used 8. Now I have 24. And who needs 6 each? Each F. So that's going to eat up my 24 left. All right, so we end up with 0. This is tetrahedral. The angles are 109.5, I believe. Now, since we have 4 of the same ligands, all Fs here, this is going to be the dipole moments going towards the Fs, creating a symmetrical compound. So this one's nonpolar. Now, if you had 3 Fs and say 1 H, well, then you're polar. Now you're polar because the ligands are not all the same, and you will create an unequal distribution of the electron density. Now, if you think about this too, if we're following the same format, the S, the P's, we have 4 things attached. That's where I get my sp3. Hybrid orbitals are sp3s. Yes?
Do we have to be equal elements?
Relatively, you need to know them, yes. But if you think about it in terms of, like on the trigonal planar ones, you have, it's a circle, 3 things spaced out as far as they can go, they're going to be around 120. Breaking that, dividing that 360 by 3 will give you 120.
Yeah.
Tetrahedral, yeah, this was kind of one you just got to memorize. Okay? So, basic just yes on that one. All right. And now we're going to look at the pyramidal. But here's my tetrahedral if you wanted to see it, because it is 3D. Okay. What did I do? Okay. So for pyramidal, pyramidal is still under the tetrahedral domain because 4 things are around the central atom. 1 happens to be a lone pair, though, so that does change things. I have a total of 8 I get to work with here. Who goes in the center? Why? Hydrogen can never go in the center. Very good. So I attach my ligands. I have 2 left. Where does those 2 need to go?
Other side of
On my phosphorus. There we go. Now, because this lone pair is up here, it's going to push the other 3 down, causing this pyramid-shaped one. The angles in between are about 107. That density of the lone pair is pushing them down, so they're no longer 109.5 where they would have been on the tetrahedral. They're now slightly smaller angled. Also, because of the dipole moments, this case hydrogens are less electronegative, so the moment's actually going towards the phosphorus here. Okay, creating that. So this one is going to be polar. And of course, sp3 hybrids. Now for the fun bent ones. This is like water. But as you see, the central atom is going to be a sulfur, so I'm not going to draw this linear shaped. It's not a carbon or a silicon. I won't draw this linear shape. I have 20 to work with here. All right, so 16 left. Satisfy your ligands first. The BRs get their 6 each. That's 12. 4 left. Who still needs 4? Sulfur. So here you get your bent shape with 104.5 degree angle. Ball and stick model looks more like so. Okay, and this is definitely polar. Now I have to check the electronegativity difference, but I think it would go out towards the bromines. I think they're higher in electronegativity than the sulfur, but I'd have to go back and look at the table of values. Okay. Now for the new stuff. Bipyramidal domain. 5 things attached, or 5 things around the central atom. So you have the axial and the equatorial plane to look at and be concerned about. So lower energy conformations result from having non-bonding electron pairs in the equatorial rather than the axial. This one's a seesaw, by the way. They actually call it a seesaw. Okay. And as you can see, the angles do change slightly here too, because if it was bipyramidal with all the same ligands and no lone pairs, you end up with 120, 90 degree, and 180 degree angles. Hybridization, 1s, 3 p's, and 1d now, all coming together. So here is your bipyramidal, and it actually forms 2 pyramids. 1 pyramid on the top, and then you flip it over 1 pyramid on the bottom. So that's why they call it a bipyramidal shape. Pyramid on top, pyramid on the bottom. Now I take off the one and I can show you the seesaw now. So here's our little purple lone pair here. But it literally is like a seesaw. So that's where they get that. The teeter is like a seesaw. Okay. Equatorial is going to be the one with just the two, forming a 180 degree. That axial is going to have like the 120. Good question, though. Okay, so trigonal bipyramidal. These ones you did draw last year, and this is where we get the expanded octets now. Why can atoms in energy level 3 or higher do expanded octets? Why can they do expanded octets? They have the d orbitals, exactly right, so they can expand. They have room to do so. Okay? So, PCl5. Right, 40 electrons to start with. 7 times 5 is 35, right? Okay. Now when I draw these, I still put one on each side first. And then I stick one off to an angle. So 2, 4, 6, 8, 10. I have 30 left. I have 5 things that need 6. So 5 times 6 is 30, so that's going to take up the rest of the electrons. Right? All done there. Now, as you saw you do have, between the outer CLs here, you do have a 180-degree angle going this way. You have a lot of 90-degree angles as well. And then between the ones that go around the middle atom, these are all 120s. So you have like 3 different angles involved here. Okay? So if you're looking at the model, let's look here at the model. It'll help you with the angles. So these 3 in the center, they're all 120s. From here to here is a 180, and then these guys all form 90 degrees. Okay, so there's 90s, there's 180s, and there are 120s in here. And that's if they're all the perfect same ligands, no lone pair deal. Okay? 120s are right here on the central part, yeah. Okay? Welcome to come look if you'd like. Now, because all the ligands are the same, is this polar or nonpolar? Nonpolar. Everything is pulling the same direction. All the dipole moments are pulling outward. Okay? And, yeah, that's pretty much that. You know, sp3d orbitals combining. You have your 120s, you have your 80, like right here, this is the 180. And you have your 90s, and then your 120s. Uh-huh. I believe so, and the ones off the central atom are the axial. Like the ones that spin around the central atom. Now for the seesaw, my favorite. We basically take off one atom and we stick on a lone pair here to what we just saw. Okay? So it forms a nice little teeter. But if you can think about them in terms of 5 things attached, no lone pairs bipyramidal, here you're going to have 4 things attached, 1 lone pair, and that's going to be seesaw. Okay, so that's another way you can memorize the shapes. And then when we take off and we have 2 lone pairs and 3 things attached, it's going to become a T shape, and so forth. So the S brings in 6, the F's 28, so that's what, 32, right? 34, you're right. Can't count today. All right, 34. We need 34. There we go. Attach your F's. All right, so 8 are gone. How many do we have left? 26, right? Now each F needs how many? 6, and there's 4 of them. So that's only 24, right? So I'm going to put on my 24. Okay. Those are a little out of their reach. Let's fix those. Okay, and this guy is kind of over here all funky. Let's fix that. All right. Now, what do you do with that extra pair now?
Put on the side.
Goes on the central atom. The extra pair goes on the central atom. That's why now we're going to have the seesaw shape. Because now that lone pair is going to push the other 4 downward away. Okay? And the dipole moments are going to go towards the fluorines, of course. But because this lone pair is up here, below the other part of the seesaw, underneath here is where the dipole moment is going to be. And so this one actually does end up being polar. If you want to see more on the model here, what I'm talking about, if the lone pair is up here, the electrons are going to pull and spend more time down here. Because the fluorines will all pull them closer down here. Okay? So this is polar. The electrons are going to spend more time underneath rather than over here. Yes? That's a lone pair.
Oh.
Lone pair. So that's where we get our seesaw with our lone pair. And I had here's a pyramidal shape one with a lone pair. So this does become polar. The angles are now a little bit off. They're no longer 90, 120, and a perfect 180. T-shaped. You would just know, that the general bipyramidal ones and then the other ones are U.S. than that, because they push them a little bit off. All right, so T-shaped. Right, 28 to work with? 28 electrons? Yes? No? Better check me. I messed up last time. All right, add your VRs. So that's 22 left, right? What? Here? CL's more or less negative, yeah. Well, yes, but since you have 1 CL and 3 ERs, yeah. Okay. So, no, I get what you're saying, though. All right, so that is now 18, right? I have 4 left. Where do I stick my other 4? On the central atom. Central atom gets 4. And now that's why it's going to look like a T shape. So here we go with our now we have 2 lone pairs, and now you have T shape. Forms a T. Literally, a T. Because the two lone pairs, they spread out this direction. And as you can see on the T shape, the angles are what? 90 and 180. There's one 180 here and a 90 here. Okay? So literally forms a T shape. Two lone pairs, three things attached. This angle is going to be 90. The one should be 180. And from the symmetry, yes, no, this one would definitely be asymmetrical, unpolar. Is that it for this one? Oh, the last one, linear one, then we'll stop after this one. We'll only have to do the octahedrals next time. The xenon compound. So, xenon brings in 8, fluorine 14, that's 22. And yes, I also know to draw this one linear, but so xenon's in the middle, and you have two things. You should draw it linear. And this is why we just took off 4 electrons, so now we have 18. That's 12, so I have 6 left. Guess where all those 6 go? On the central atom. I just know, well, and let me show you why I know to draw it linear. When I have all these extra electrons, so this one's a straight line.
Yeah. So if you drew it then
not if you have the dots in the right place. But as you can see, linear, straight line, right? Nice straight line, nice 180-degree angle. Linear. Now this one though is interesting in its polarity. Is this one polar or non-polar?
non-polar.
Non-polar. It is symmetrical. Look at your dipole moments. They're equally pulling on the central atom. So this one's non-polar. Your degree angle, 180 degrees. So just because it has lone pairs doesn't automatically make it polar. Most ones with lone pairs are polar. However, in this particular case, you have to really look at the shape carefully because they're equally pulling on the central atom. So this one, the dipole moments make this one non-polar. Okay? So keep that in mind. Sure.
This one, these are equal.
No, because you have like one other thing in play. So that's why. Oh, yes. Sometimes. Sometimes I like to